Okay, so now we've calculated, used a calculation to determine formula of a compound, empirical formula, and then onto molecular formula, possibly. The kind of next general topic we want to address is sort of combining the two pieces of information we've talked about so far. We want to combine the information in the balanced equation with the types of calculations we can do that relate things like mass to quantity. So what we're going to want to do is a unit conversion type calculation, but we're going to want to add in quantitative information from a balanced equation into that calculation. I've got a couple examples here on this page, but let me just first point out with this equation, right, the equation says 2 moles of potassium chlorate reacts to give 2 moles of potassium chloride plus 3 moles of oxygen. There are several relationships in that equation that we could use in terms of a calculation. So 2 moles of potassium chlorate react and produce 2 moles of potassium chloride. So we could use the information present in this equation to relate those two quantities. Now we could flip that over as well if we wanted KCl on top, KClO3 on the bottom. We could do the same thing with oxygen. We could say for every 2 moles of KClO3 that react, forgot moles there, we produce 3 moles of O2. That would be an equality. So we could use that information that's in that equation to relate moles of KClO3 to moles of O2. We could flip that over. Since it's an equality, we could have 3 moles of O2 on top and 2 moles of KClO3 on the bottom, right? We could also use this to relate the products. For every 2 moles of KCl that are produced, 3 moles of O2 are going to be produced. And that could be turned upside down as well. So once we have a balanced equation, there's a lot of information contained in that equation that we could use in a calculation. Okay, so let's do a couple of examples and see how we can use this information. So we've got a little bit of a description here of the reaction. Decomposition of potassium chlorate can be used to make oxygen in the lab. Okay. How many grams of O2 can be prepared from 4.50 grams of KClO3 or potassium chlorate? So we've got a sample of 4.50 grams, and it's potassium chlorate. Right. And now what we want to do is work our way to grams of O2. So we've seen, if you start with grams, you can get to moles. Well, whenever you see a balanced equation, moles is going to be something important because the balanced equation is in terms of moles. 2 moles of potassium chlorate react to give 2 moles of potassium chloride plus 3 moles of oxygen. So if we can get to moles, we can use any information in that equation. So I'm going to cancel out grams of potassium chlorate, and I'm going to change my units to moles of potassium chlorate. And I just need to go to the periodic table and look up some of the pieces to know what that mass would be. So I've got a potassium, a chlorine, and 3 oxygens. Potassium is 39.10. Chlorine is 35.45. And oxygen is 16, but 3 of them would be 48. So again, all that's coming from the periodic table. So remember to look at your friend, the periodic table, when you're trying to find that type of information. And add those together, and I get 122.55. So 1 mole of potassium chlorate weighs 122.55 grams. Now that gets me to moles of potassium chlorate. Here's where I can use the balanced equation, because in the next step here, I know I want to cancel moles of potassium chlorate, right? Just because that'll get rid of the units and give me a new unit. But what I can do with the balanced equation, every 2 moles of potassium chlorate are going to react to produce 3 moles of O2. So I can use that ratio to change my units from describing the sample of potassium chlorate to describing the sample of oxygen. And those coefficients from my equation are the numbers that are going to go in there. Moles of KClO3 cancel out. Now I've got moles of oxygen, right? And now all I need to do is get back to grams. Well, if I want to cancel moles of O2, I put moles of O2 on the bottom. I can relate that to grams of O2 using the molar mass of the O2 molecule. So 2 oxygens would be 32 grams in a mole. Moles of O2 cancel out. Now I've got my answer, grams of O2. And again, just like we saw in chapter 1, all the math there is laid out. Right? We want to be careful not to miss anything. 4.5 divided by 122.55 times 3 divided by 2 times 32. 3 significant figures in my original mass, so I can keep 3 in my answer. 1.76 grams of O2 is what could be produced from that reaction, right? So first step and the last step there are the ones we've been looking at earlier in the chapter. The only thing new is this piece in the middle, right, that converts from one of the components we're looking at to another. Now, one thing that I think I probably should be pointing out right here, right, notice how explicit I am in writing out my units. Grams of what? Moles of what? And that's important because of this step right here. Right? It's going to be important in a lot of cases, but particularly here, if you take those away, right, particularly if you took it away back here, right, moles of what? Is it moles of KCl3? Is it moles of O2? Are you done? Are you not done? Do you need another step? Right? The more explicit you are with your units, the less likely you are to maybe think you're done with a problem when you really aren't, or to end up with an answer that doesn't really match what you're looking for. So highly recommend, right, take that extra second to write out your units a little further. It'll help as you progress through the problems. Okay, another example here, propane, C3H8, used for cooking and heating. We want to calculate what mass of oxygen, O2, is consumed in the combustion of 1 gram of propane. So we've got the mass of the propane. In this case, we're trying to figure out how much oxygen do we need to react with it, right, to convert it into the products here. So again, we start with the mass, 1 gram of C3H8. If I get to moles, I can use the information present in this balanced equation. So 1 mole of propane would weigh so many grams, right? And again, I've got that formula. I can look that up. 3 carbons, 8 hydrogens, so I know the pieces. Again, I find carbon in the periodic table. It's 12.01, so that would be 36.03. Hydrogen, there's 8 of them. It's 1.01 in the periodic table, so that would be 8.08. And that would be 44.11 grams per mole. So 1 mole of propane is 44.11 grams of propane. Right. Now, with my units as moles of propane, I can think about the equation. 1 mole of propane is reacting with 5 moles of oxygen. So that can go in as the next step in my equation. Excuse me. 5 moles of O2 react with every 1 mole of propane. And that, again, that's going to cancel out moles of propane, leave me with moles of oxygen. And since I'm looking for mass, it's kind of same last step as in the previous problem. I want to cancel moles of O2 on the bottom. 1 mole of O2 would weigh 32 grams. And that would get me where I'm trying to go. How much O2? So again, I just kind of have to do the math. 1 divided by 44.11 times 5 times 32. And I'm at 3 sig figs again, so this would be 3.63 grams of O2. It would be needed to react with that quantity of propane. Okay, pause the video there. We'll go on to the next page and pick up on the next page.